Okay, it's interesting that luckily enough there's been one or two talks before, Peter's was relevant in this sense. I can look for the differences in the way of going about the subject, not just the content, but the approach to what we think we're doing. And in fact, I think the distinction I would spot is that rather than using the toolbox of maths to just expand the models and see if they agree, it's more a matter of recognising shortcomings. It's a peculiar time we're living in when there seem to be shortcomings in the physics. I speak from an engineer's point of view where those shortcomings affect the way you can go about understanding, applying and approximating. So it's a fairly rich opportunity to look for exceptions, possibilities that are out of line. And that is not so much a matter of evaluating lots more, it's a matter of looking for the basics to see if they're misplaced, if the foundations are out of line. So I did that by just studying electrons. Electrons are what engineers are interested in. Strength of materials, you've got biology, you've got photonics, loads of it. And half the engineering world and a lot of others is about electron fields really. The rest is for luxury. So starting from that, I found some problems there, not the least of which is the fact that the electron fields, when you mix them, if you try and write any old sort of fields, you can't account for why they fluoresce with a down conversion but not with an up conversion. In ordinary physical systems, that is very hard to achieve. It's only in very special circumstances that happens. It's used in engineering as it happens for modulation processes, but they're a very weird thing that you have to put together in the right way. So that interested me a lot, that the model doesn't even acknowledge this. What happens in physics is they work out each individual electron because if you want to put them together, they do the wrong things. So they don't put them together, they work them out separately and then add the results afterwards. Well, of course, that's nothing quite like the same thing as working out what the interaction effects are of electrons built on top of one another. So I was inherently, from the beginning, looking for a model where we could use a single Hilbert space and populate it with these eigenmodes on top of one another, as opposed to separating them out, working them out, and then adding them up afterwards in a 6n dimensional Hilbert space for n particles, which is the way it's done in quantum mechanics. However, that lot was a prod at the beginning and affected a great deal. Caused me to introduce a Hilbert transform into dynamics, but perhaps deeper things coming out about the approach to these things. This revisiting Isaac Newton, we're not talking 20th century at all, we're just revisiting Isaac Newton and look at how he makes models. We're looking for a fundamental model here. Even though I speak as an engineer, I want, if possible, a fundamental model. If I can't find it, I want to know where the approximations have to be. Well, the reason you use approximations is either because there isn't a fundamental one to hand, or it's just too laborious to work out the fundamental one. So either would do, but you set out on a quest looking for good approximations with the sense that fundamentalness matters. Now, fundamentalness means the model speaks to you. It's not just that you use it to sort of calculate something you're sure about the structure of elsewhere. It's actually got to carry the structure in it. And the problem I find, the most blatant one, and there's a few others, is the fact that, I'll give you two. The Newtonian one's first, in historical order. The Newtonian one is that he starts by inheriting the dynamics of a mass and energy-based system, some sort of momentum-based, and then he overwrites it with a field system. Those two are very different in nature. Fields are about propensities. You cannot observe fields, otherwise they're not fields. We live in the matter, and our observations are caused by changes in state of matter which are then amplified. If you're not doing those two things, then you're not observing. There isn't an observation that isn't like that. You sometimes don't have to amplify because what you observe is like a ton of metal moving a millimetre. You can often do it with the energy that's in the process, but that's a very special case. The ones we're looking at for microscopic observations anyway are always a change of state of matter followed by an amplification. And if you haven't got those, it's not what I'm talking about, and it isn't in the game anyway. The issue of amplification is neglected totally by philosophers and only dealt with peripherally by physicists. For me, it's key to observation. You must have amplifiers for microscopic observation. And amplifiers can only be built in certain ways and have properties of their own. So we go on down looking at what might be possible in this area. Let's get the two anomalies. He's invented energy which is in a quadratic space of the dynamic variables. If you have waves, then energies come in as quadratics on them, and the same it's the same with mass, and it's the same with charge. So we know that if we're to have a linear model underneath, it won't have to have energy, and energy will have to emerge from it as embedded in its quadratic nature, in the quadratics of its nature. That means inner products. It's the inner products that give you mass, energy, charge. There is potentially a linear model underneath, but of course we start with Newton, and he puts energy in. Not only does he put it in contradistinction to a propensity model, as I call it, a field, but he also splits it into two pieces. And models that are made by entities are alien to models that are made by propensities. Ron Harry writes a little bit about this. These are the poles of modelling. If you're going to have fundamental models, they've really got to be, if possible, pure propensities. Whereas working models are nearly always, to some degree, practically, they must always have named items in them, in fact, and simple rules for doing things are made nothing but entities. So we really want to keep the entities out of it, this model. That's so much for the fact he's mixed the models and he's gone and split one of the categories beforehand. You shouldn't split any, you shouldn't even generate entities, let alone split them, because that must emerge from the nature of the model. You can see it coming, you know? And yet the Lagrangian, which is religiously adhered to, starts with the basis that you will use a variable that's the difference between the two forms of energy. That's cooked it before you start. That won't go. You know that therefore it'll only deal with real variables, because if you put complex in, it kills off one of the two parts. There's no good at all. So in fact we then start to look for how can we get a model at all. It's going to be a reasonably simple wave model. We don't want to start with particles. The other problem with particles, of course, if you use those as a way of extending Newton, is you're going to get infinities all around them because they've got infinitesimals as you approach them. We're interested in finite bandwidth models that only work up to a certain frequency, because we don't want to postulate anything faster than some limit we can name and say, well, forget it about that because it couldn't matter. The one we look at in fundamental physics is the Planck frequency, or a few octaves above it, you know, that's about it. If we can work to that, then we don't need to approach any limits closer than that. Okay? So what do? We try and simplify this thing. What's the nearest model for electron stuff that we might have? Well, of course, de Broglie introduced a solution to a Klein-Gordon equation, a linear dynamic solution, not the Lagrangian solution like you see in typically Schrödinger or Dirac. He introduced it as a plain dynamical equation to give him, well, I don't know whether he did it that way, but it's reported that way, to give him the rectilinear plane waves that associate with moving particles. So an obvious question, obvious. Why don't you take the equation and solve it in all its glory instead of associating it only with rectilinear motion? And you say, well, okay, let's try to do that. Write it down, expand it up a bit, you know, get the thing going. And then you start to say, now we're going to have to make sense of it because the electromagnetic field affects it. So it's going to be a matrix equation. So what time did I start, by the way?
About 33 or something. About 33.
Okay, thanks. Yeah, so we expand that up a bit and then find we're going to have to put the coefficients in, and you think, oh, we'll take a Faraday matrix, you know, somehow. And then you find, well, it's not working, it's a bit of a mess, because it's actually got elements, some of which are polar and some of which are what we call them, pseudo-vectors. So that's a bit of an oranges and apples thing. Can't we put something together that's made of the same stuff at least? Looking at that, it took me quite a while looking at that and really trying to form equations that would make sense, even let alone give us decent solutions from the Klein-Gordon, until in the end I realised that the Klein-Gordon equation has got a differentiator in front and a differentiator behind the operating matrix. And if you look at the Hermitian form of it, it cancels the multiplier when the left-hand differentiator is differentiating the matrix and the variable to the right. You expand it into two terms. One of those terms is nullified by the Hermitian form, the other one is left, and it creates structure. That structure is not there at all in the canonical approach to quantum mechanics. So, great, that's interesting. We're now getting an interaction result at the linear level underneath. So, go on with that and close the electromagnetic field. Now, the electromagnetic field, we've got to get the electromagnetic field out of charges and currents. Now we can specify in these moving waves. We can do ordinary sesquilinear, bilinear complex products. Give us all these velocities, rates of change. They're all quadratic, so they're all in the observable domain now. We're defining the thing in the linear domain, and then observing it in the sesquilinear domain, bilinear domain. That fits in pretty well with general concepts of modern quantum mechanics, but it isn't what's done at the beginning. People start with energy in the picture, and you really mustn't. Energy is derived from the picture. So anyway, what do we get? There's lots done in this area. I just want to try and cut it off at some reasonable point. You can see how much objection there is to using Newton as is. I've bypassed that. It talks here of a substrate model. What we find is because we've got two sorts of non-locality at large in physics. One is an effect of apparent simultaneity at a distance, Allen aspect and all that stuff, EPR, and it is, as it happens with this model, it is accountable on a causal basis. It's just that you can't do that when you use photons, because you think of the photon arriving and depositing its energy. You have to have a continuous field, and then you'll get correlations in the multiplicative processes at the end. They're not additive processes like a piece of energy arriving and adding to the state or something. They're multiplicative waves that cause the two end processes to modify in certain ways. And because the phase shift is proportional to frequency over a spectrum, if you in the middle put a down converter, a degenerate down converter like we do in the ordinary EPR experiments, it inverts the spectrum of the two ends so that the process of lagging in time is matched up with the one at the other end, and then the correlations appear at the two ends. You can expand all that out, and this is just not in the model for ordinary physics now. The photon ruins that. Hence another interesting continuous methods. Now, where am I going from here? A substrate model. We've got to generate somehow a way of getting, if possible, a unification between the electromagnetic field and the thing it operates on, the matter. The electron is what I'm talking about. Now, one of them is in the nature, it looks like a set of quadratic a set of correlational relationships, a matrix, that's the electromagnetic field. And the other one is some sort of resonance state, like a little bottle of something resonating. We've got to get both those out of the same field. And it turns out that then if you postulate a high-speed wave and you fill it with random noise, near Gaussian, you give it a slight disturbance from Gaussian, something's causing it to be not in equilibrium, overpeaked and overtailed. That will cause it to have positive kurtosis. Positive kurtosis means that any scattering process at a weak level will release energy into the scatterer. It's a heat engine. That, in fact, is very much like the way a heat engine works. It's an abstract sense of how a heat engine works. And that means as long as we can get kurtosis into this underlying random field, then the depletion of that kurtosis is capable of keeping something in an active state. Now, since our models are not perfect, I mean, we've got singularity at the centre, and yet I said we're going to find that bandwidth, the limit of the Planck frequency. It means there must be degenerate scattering as well as coherent scattering. the coherent scattering is by far the majority, because the frequency of the Planck is so high that you only need it to break a little bit of glass at where the zero crossings are in order to keep this lot going, just like an engine keeps going in spite of the fact there's friction in the bearings. It's a small factor, and in the case we're dealing with here, a very small factor. That sort of completion of the model is feasible, and it's got the right structure at any rate. It's that which I carry on studying. Okay, we've looked at the sort of problems that came from Newton. We can bring them up to date by saying there's an unnecessary gauge theory in electromagnetism. Electromagnetism was introduced by Maxwell and others on the same basis that Newton introduced gravity, which is simply as a field continuing to operate on the entities, the substantive entities. So we've just got more of the same there. But the inheritance of study of the electromagnetic field include uses of the electric potential, I'm sorry. The four vector used to describe the field has got the magnetic vector potential and the static electric potential to form the four vector. Well, these are alien to the system. For a start, if you're going to produce a space integral for the magnetic vector potential, you'll need to produce a time integral for the electric potential, and they don't. They're both space integrals. That's alien. It turns out that if you do use a time integral for it, it fits the equation I'm using. So in fact, we shouldn't be using electric potential at all. We should be using an antiderivative, I call it, of the electric field. You can then go ahead and find the results are consistent. You don't need a gauge theory treatment for electric field at all. That's just completing the relativistic sense of it. It's only because we don't want to use relativity that we keep having to refer back to electrostatics. And in fact, it's apparently quoted as part of the canonical form of quantum mechanics. It's a great spanner in the works. Okay, we take that out, and we move ahead. There's other gauge theories around. I have my doubts about them. It doesn't matter much at the moment. We're just getting through the basics of this. So I don't think there's anything much to be said. Basically, we don't want to use Lagrangians at all because they've got pre-defined species of energy, and you shouldn't do that with a model that you can make at a lower level of energy. So it's the underlying layer I'm going to talk about today, because if you want to, you can read reference 1 off this sheet, which is on the web. It's a thing called ripple-.pdf. And it will give you the stuff I've just been talking about, and agonising. Well, 100 pages of it, could do with another 500 pages to make it complete, but anyway, it gets to start pretty well. So, yeah, just let's have a look at what we're saying here. We use the Klein-Gordon substantive wave model for electrons. The result obtained in this way is just a deeper form continuum model that, in case with conventional quantum theory based on particles. The deeper one is going to be this unifying field, which I want to talk about. I hope I've got enough time to do some of this. It's interesting, this man called Palash Pal, who I just recently discovered some of his stuff, he offers a conceptual unification across the notions of fermions, the Dirac, Majorana and Weil kinds, and but he starts out from a Klein-Gordon equation in the Lagrangian. With the result, he's going to only have real values. That means he can't go any further with it, unfortunately. So that's because he can't get away from the fact that the energy types are different. He applies it to real function. Let's just see what happens. What we're doing here is use the Klein-Gordon equation to set the complex scalar continuum field, and the fermionic eigenfunctions can then be dropped out. It's just how, if you work with that type of complex field, you can go further with the same model. You mustn't get near a Lagrangian. But causal flow. Let's try and start giving you some of this stuff here. There's what we're going to be working with on electric field. We're going to need a way of getting the electromagnetic field from the state of an electron process. That's the interacting fields, the superposition of fields, and I mean real superpositions in a 3 space, not in a 3 times n space or a 4 space. Okay, I do mean a 4 space. I don't mean a 4n space. So the first thing here we've got. Let's just get my pointer to do this a bit better. So we've got. This is a vector of 4. It's a charge in 3 currents. They're all, okay, they're just all scalars at that level. We've got psi star times psi. This is a general differentiator, a 4-dimensional differentiator. And if you multiply that one by that one, you get Schrodinger's wave intensity. If you multiply that one by the derivative, time derivative of that one, you get Dirac's field derivative. But what we do here is put a Hilbert transform on that, and then subtract the same thing with the commuted form of the Hilbert transform. And what that gives you is something which is sensitive to positive phase shifts in positive frequencies and negative phase shifts in negative frequencies, or vice versa. It's just differentially sensitive to the 2 signs of frequency. And that produces the results that we observe with electrons. You don't have to put together a superposition rule based on the 6n Hilbert space and all that. If you take the Fourier transform of the frequency side of this, which includes h is a temporal effect, that's the Hilbert transform in time only, then these 2 signs are the form that Hilbert transform takes when you Fourier transform it. So this is a much neater thing actually. This is a hybrid, this is the same vector, it's an identical vector being evaluated from the field seen in the Fourier transform of its temporal process and the actual physical values of its spatial processes. It's a hybrid transformed variable. Most engineering of dynamics is done with the temporal process in the Fourier transform and with the dimensions as they are normally. It's hybrid. And yet nobody uses the term hybrid Fourier transform. They just never think of transforming the spatial stuff. They just don't do it. Okay, when they talk about a Fourier transform or a Laplace transform, they're applying it to the time only. Okay, and I call that hybrid. Okay, because you can apply it to all 4 dimensions if you want, but it does you no good. This is a good way to work, and for me it's imported from the way you normally do control engineering and that sort of thing. So we've got this peculiar effect of the sign of the frequencies being a first order multiplier. It inverts effects, and this causes differences in frequency to produce a result in here, but sums in frequencies don't produce anything because they will be opposite. It's not that, the sums, they must be of different frequency. They're all sums, but when they're of opposite frequencies, they produce nothing. When they're of the same sign of frequency, they do produce results, which is what you see in electrons. That's what electrons do. They don't produce any sort of gamma. They only produce down-converted visual light through the mixing of their mere Compton frequency oscillations. That's a most peculiar effect, and this is the mass that represents it. It's not in ordinary physics. Instead, they cut it out by saying that's not how you add the numbers up. You just break the process at that point, plug in the individual electrons, and then say what they do and add them up afterwards. Unfortunately, you've thrown the interactions out the window at the same time. That is hopeless. Okay? So we've gone. That's a general model saying all this stuff that I was putting on. You've got 2 wave systems. There's a wave variable there with its wave rule. The wave variable here, that's the psi wave, scalar complex. You've got this electromagnetic 3 real, or whatever you like to think of it as, operating there. The state of this one impinges on that to create its coefficients. So it's a order 1 multiplier on there. the charge origination comes out by the rules I've just shown you, and the magnet origination. And that gives you electric charge density and electric current density, which is a vector. There's three of these, it's a vector, this is a scalar. There's a continuity relationship operating there, so you're not free to put those in independently, they must maintain continuity. That creates an electromotive force and a magnetomotive force that come and create the source of this wave, the electromagnetic wave. We've got a complete closure here. This is a quadratic derivation across here. We saw them just now, the sesquilinear psi star psi, that's quadratic. And this enters as a first order coefficient in here. So this loop, or this loop, whichever one you like, is cubic. That immediately gave me encouragement that we are in the game to find solitons. Static excited level solitons mean cubic. They cannot be less than cubic operation in their feedback loop. So, yeah, I don't know what I'm doing here. I think I need to, I'll let it come down a bit. So, where do we go? We're going to now try and put together the Klein-Gordon equation of the sort that we want. And in order to do it, just as ordinary quantum mechanics uses, it modifies the electric field by integrating it, and it integrates it over space to give it what would be the electric potential. What we do is integrate it over time. We get this funny variable, which is not very imaginable. It's just, I just call it G, but it's being integrated all the time along the time axis. Similarly, that's an integration process. Similarly, we go from H to the vector potential, which I call magnetizing 3-vector here. That's an anti-curl. That's an integration in the curl sense, a three-dimensional integration. So we've got spatial anti-curl, and we've got spatial temporal integration. Now that's uniform across the relativistic sense of the thing. We're going to use these as a way of getting into the equations, but we will need the magnetizing one also in the starting point to be once more integrated. Remember, there's a left-hand differentiator that will get rid of our unwanted integrals. This is synthetic integration, which will, when you evaluate, multiply out the equations, is going to make it disappear. So don't worry about that. You can just do it for convenience, because you need it if you're going to use a matrix to show what you're doing. Here we are again, if this will work. But be careful not to press the button, because it goes and takes a measurement. Nice button. So we've got, it will work out on, I'm sure. Maybe the battery's on the way out.
That's what I thought happened yesterday as well.
Yeah, I think.
And I switched it off and then it worked again.
Normally pressing, yeah, switch it on and off with the button now. So, okay, so here's these pseudo-integral things. First of all, we take Fourier transform on it, as in most engineering. Now we've got these capital E's, we use capitals for the Fourier transform, which is that means the Fourier transform is, what we've done is multiplied out to an omega. That's all it should be. It looks like it should be capital G. I'm caught at the moment because I can't read that. I've read this hundreds of times at the moment. Anyway, we get the electric terms along here, and they're in their Fourier transform form. The magnetic stuff has got J's in front of it, and they stay there for now, and they stay here. But these are differentiated once too far, integrated, sorry, once too far. And my question at the moment is why those are not being shown as capital G's. I wonder if that's an error. It's conceivable. Anyway, not to worry for the moment. You see what I'm doing? They're basically putting it back together, and you end up with these. These are the equations after we expand them up and transform them a bit. Let's see what we've got here. I should have bought some battery first. What was that today?
What size batteries do you need?
They're AAA's, I think. These are very low grade AAA's. So, the middle one's interesting. This is what you get if you expand those equations out that I gave you to give you Gibbs type vector notation. I've introduced a var pi here. It's a pi symbol, they call it var pi. And it conveys the charge. The charge in this is not a la Dirac due to the positive or negative signs of the eigenfunctions. We need the entire eigenfunctions. It's fundamental to the solution. We need all four parts. So how do you get the antimatter? Well, that comes in through the substrate I talked to you about. The substrate excites these systems and keeps them excited by its general level of excitation. And the normal way to think of that is it bombards the electron vibrating process which scatters. And the scattering comes into equilibrium at the level at which it just depletes the kurtosis of the amount of field that's being scattered. That reaches an equilibrium that causes the charges all to be the same, because that's got the same process in a multiplicative sense as you get in the equipartition of energies in an additive sense in a pure thermodynamic system. This is a meta-thermodynamic system where the interaction is a multiplication, not an addition. And the result is that the equilibrium states are proportionate to frequency. Instead of all being equal, they're proportionate to frequency equal. Okay, that introduces that mechanism introduces H omega. No luck with the batteries?
No, sorry.
We've got a little bit here. Okay, so this is a steady state one. This one has kept the Laplace transforms in. There was an omega I should have been able to divide out of that other one, and that's why we had e's in there. I can remember where it disappeared. I haven't got the time to find where it came from, where it was. So this is perfectly legit stuff, checked through there many, many times. You see we've got the electric and magnetic Laplace transforms in here, which means you can study, for instance, fluctuating light applied to the electron with this lot. If it's steady light, this will do, because you can express that just as constants. In fact, it doesn't have it's a single spectral line, and you can just work. The steady state comes out like that. If you put in the dimensional stuff, SI units or whatever, this is the thing you would use to get, you can see sort of charge on the electron and things appearing. Okay. What are we doing? We've got half an hour, haven't we?
Yeah, about
All right. Pardon?
a bit less.
Okay. So here's if you take that wave equation I gave you, which was for electrons, treat it for any electrons, because they've all got the same local Compton frequency, you've got these four major separable factors in each eigenform. The harmonic, the usual quantum harmonic, it's got three quantum numbers associated with it. That's the spherical harmonic. Then there's a ripple factor. The cubic factor term, which I told you is in there, can be separated out. And it's common to all of the modes. It is delightful. It's common to all the modes. It comes straight out by itself. It's totally separable. That means that it's a real variable. It means it can only run from radius to periphery. You've got an azimuthal equatorial domain and of course a latitude domain as well. But the ripple runs radially. That means it's a one-dimensional problem. At first I thought it was too good to be believed. I was trying to work out one-dimensional approximations, but actually it's a one-dimensional problem because you can extract all the other variables and get them off and just solve the thing in the radial domain, so long as you don't have any distortions of the spherical form. So for an isolated atom you're in a very good position. So you can get started on this work straight away. If on top of that you make it a neutral, a noble gas, it's got no magnetic field as well on the electrons, so you can actually just work out the electric stuff. That's really very nice, and that's what my colleague was attempting to do with computation. He's not come up yet with much of an answer, but anyway, that's good stuff. Spin factor, well, when you look at this spin factor, it's got 4 parts, not 2, and that's enough to actually synthesize it topologically. We can tell you what the shape of it is, we can tell you how the phase varies around the azimuth. You only need to study one circle of the azimuth because that's where it's all happening. But the points about these things is the spin factor has got a half twist in phase and a half twist in amplitude. Okay, it's amplitude complex. And that makes a full twist. So it's continuous in the cycle. But the two variables will be inverted after one turn and come back to where they were. So you can see the two revs to get everything back where it was. That's completely topological. You can draw sketches of it and everything, and I'll give you the expressions that will show you what the variables are like all around that. Okay, I'm rather pleased with that. It makes spin tractable in that sense. I'm talking about spin in the solution domain, not in any algebraic domain, either separated symbolically as a result, or in the form of the equation, because the form of the equation hasn't got it separate, of course. It's just part of the form of the solution. And then the Lorentz velocity factor is simply a phase twist, dependent on the frequency, and it causes things. When you put a twist in, it causes things to be moving. That's fairly straightforward stuff. The ripple we can see here. I'll get a moment to point at it. This is the form of the ripple function. Notice it's a function of x only, whereas Gn, which is the residual vibratory stuff, this is the modes, and there's an n under there, because this is n modes of electrons. And also, HL enters this, whereas you can solve this by itself just based on what is the charge. That's the divergence of the electric field, which means it's the charge density. So if you know the charge density, you can solve for H. Okay? However, you've now got to work out what it appears in here when you do your residual, solve all your spherical modes. But of course, you can do this on an approximation basis, solve for this one, and then with this result, go back and get a more accurate result on that one. So you've got an iterative solution possible there. And that one is relatively independent of this. And I can show you later a one-dimensional solution with this replaced by a simple hyperbolic tangent. I think a simple little hump function, which is about what these are like anyway. And the solutions of that equation, the first one, the ripple equation, are remarkably tolerant of giving it weird things to integrate over. Almost everything will quantize, but it will only quantize if the integral closes at the end. You integrate it over the axis from origin to periphery. And the only quantizable situations are ones where it starts from nothing, which it must, and ends at nothing because the integral happens to take zero at the end. So you do an iterative solution and find, and then count the number of cycles you've got. And it will close for any integer number. That gives us a basis for finding entities that will quantize, but not what value they'll quantize to. In order to find that out, we've got to look at a stochastic process that is in this underlying wave, which is what I'm trying to bring you to today. There's the radial solution. You can see the hump, grey hump in the bottom there, and the radial solution along the top of the h function. It's h squared that is actually used in the effective, and it's a real variable. And because can you see how pointed it is at the top of each cycle and how straight line it is across the axis? By the time you square that, the zeroness of it around the crossing point is very strong. It's up to it's got zero derivative up to about the fifth, and that is ideal for what you want for the decoupling of vibrations in adjacent resonators, so they can have a proper linear eigenfunction over them, but they don't interact more than a very small amount at the junction. Where they interact, you'll get degenerate radiation. Degenerate radiation has to be made up by a slight overdriving of the scattering process. It absorbs energy and is made up by the energy being used up in the space in the substrate wave. So this is zero diverging we're talking about. That thing can be written down or in any of those forms. There's the signal flow graph for it. Notice that the equation suggests everything flows one way and it's all held at zero. Well, there's no such thing. You can't all hold anything at zero. This says you can write it down with all the flows in space derivatives going one way and integrals in time derivatives going the other way. That is an ordinary piece of realizable mechanism for any wide band of frequencies. is stable up to, if you don't have faults in those differentiators and integrators, it's stable up to infinite frequency. However, if they're less than ideal, then so long as the bandwidth of the noise, that f(t(x,y,z), can you see it there? This function here, as long as that is finite in bandwidth compared with any imperfections in these, that thing is stable and keeps operating. In fact, as long as the imperfections in these roll off at a certain rate at high frequencies, the whole thing is absolutely stable. If you try to make it reverse these arrows, then you cannot realise this point here. You can't have three arrows with equal values producing a result that has had that equal value. The only way you do that is with some sort of controller with infinite capability. So this is the only realisation of the D'Alembertian that works. Okay, so that's the one we're using. That means that since those arrows are implicitly in that form, this equation has got a kind of arrow of time. However, the solutions are symmetrical across the directions, so it seems to have no direction in time. That is still does not stop it from injecting an arrow of time in its parameters up onto the upper model which I've been talking to before. So this thing can't itself generate an arrow of time, but it's got the machinery in it to cause its parameters to show it. And that means that we have got a model here that shows the arrow of time in our ordinary observable world. Because it starts from this, which produces it through its parameters. The other model is the parameters of this model, stochastic parameters of this model. Okay. No, I'm following anything like what I'm saying here. Kurtosis, well, the kurtosis I've talked about now a bit is the deviation of the Gaussian spectra from their perfect form. Over-peaked at the centre and over-amplitude on the tails is positive kurtosis by the normal convention, and it's that which needs to be depleted in a form of heat engine operation. There is negative kurtosis as well. In fact, the electron has got two frequencies, positive and negative. It's got two rotations, so it gets a type of oscillation along any line in the complex plane, what I call a bicissoid vibration. Real is along the real axis, but when you allow the phases of the two components to be anything, it can be on any axis. And it's that class of functions that are found in the electron model. And what is more, that angle moves as you go round. It goes through half a twistor in the azimuth, for instance. That class of solutions, having parts in opposite frequency, and then two other terms at zero frequency for the steady state, anyway, complete a solution of the equation. Okay, that D'Alembertian, that Klein-Gordon. So the kurtosis is carrying all this. Kurtosis can be generated by the system. I'll try and take you through that. The metathermodynamic solid state attractors, because the kurtosis can be absorbed completely by scattering only a small amount of the field, that is the amount that gets scattered, because if it's scattered any more, it's attenuated. It's rather like the Higgs mechanism that's got a natural level of excitation above which it will come back to, below which it's excited up to. It's got an emergent nonlinear effect in a linear system because of the stochastic nature of what's going on. Okay, its process of kurtosis in the lower model manages to induce nonlinearity in the upper model. It turns out then that if we look at that system and consider that we know there's three leptons, then it turns out, let me go a bit further through these. This is what happens if you take that same D'Alembertian causal flow and put all the cross terms in as well. I've marked all the cross terms the same, zeta, and all, I wonder it, and all there's the other ones going back to a direct closure as eta. You've only got, that's the electric terms and the magnetic terms respectively. Of course they don't have to all be the same, but we can study them like this, and in any case for symmetries they're likely to be effectively this, at least stochastically. So we then are able to ask, because you've got all the problem of understanding how that comes about. Well, there's two senses in which this closes. You've got the closure of the general matrix, which has got a characteristic equation associated with it, it's a cubic characteristic equation. But the other one is in structures of closure. You can go through this. You can go through this thing, always coming back on the same path you went round. They're all in parallel, and that's what you call first order closure. The zeroth order closure is unit. The variable is what it was. The first order is got to come back at 1 when it's closed like that. The second order is allowed to go 1 across and then come back 1 back. And then the third order goes 1, 2, 3. And those three solutions of this as a stochastic process are independent. And they all have resonant frequencies. And since we've got 3 leptons, it looks as though they may well be associated with them. Then, knowing that we expect this wave to be travelling fast, we find that there's a completing factor coming from that speed. And when we put those together, it tells us that the speed of the wave is around 10 to the 7.3 times the speed of light. Then this mechanism falls together and is capable of solving for these various effects. Anything else I can show you up here? Here's some of the kurtosis calculations. They're just this is the mixing process. Since the electron's got 2 spikes at plus and minus frequencies, that is the most negative kurtotic form that you can have. It's got a kurtosis of -3, and there isn't anything more negative than that. And what it does, it takes the substrate spectrum and shifts it, half of it up and half of it down, and that causes it to get a bit blunted in the centre, which is a removal of positive kurtosis. And that's a really quite algebraically intact process. It's a fuel-efficient system. If your heat engines worked as well as that, you'd be well pleased with them. You can see then how there's noise of kurtosis, which can maintain the system. The question is, how does the kurtosis get there into the spectrum of the universe? Well, if you're in a relativistic universe, you've got a mixture of local stuff and remote stuff. And the more remote the stuff is, the lower its frequencies will be. So if you mix local, central peaked stuff with distant, more flat Gaussian, that mixture of Gaussians is positive kurtosis all the way. It's positive kurtotic. So the aging process of the universe creates kurtosis, and the scattering process of the electrons destroys it, and those two are in equilibrium. And in order to hold them in equilibrium, the scale can go up and up until you reach a certain distance where you will have reached sort of neutralization of the equilibrium, the system, the game is complete. Within that area, the things all attract, and outside that area, they keep themselves to themselves, and there is no gravity. Which means that you'll get galaxies, and it means that they will show dark matter at the edges. Okay, so that's the basis. Okay?
10 minutes.
Okay. So did you track that sort of model? Have I said that to you before? The way you can see how if it's kurtosis that's driving, then the rising frequency of the universe maintains the kurtosis. Of course, it gives you redshift as well. It means that you can see in the electromagnetic wave, which comes to us so slowly, 10 to the -7 times the speed of the active wave, you can see what the universe was doing all that time ago, and it's very red in the distance. Meanwhile, we are blue shifting all the time, gradually blue shifting, because our scale is made of the Planck scale. As the Planck waves go up in frequency, we get smaller, because everything we're made of is scaled to that, because of the processes that are maintaining that vibration that I went through just now. So this is the sort of ordinary multiplicative operations on the spectra. The cumulants are what you're really interested in. The second cumulant is the variance, which is only dependent on the speed of the ratio of the speed of light to the speed of drive waveform. The fourth cumulant comes out as a double closure. It's a second order process, that's why everyone doubles. And then the sixth one is active as well. So you've got the fourth and the sixth, and the speed of the underlying wave, which give you the three lepton frequencies as it appears here. They're just the cumulants you want. Any other cumulants are of no significance, because the reason for this is because a differentiation n times decodes the nth cumulant. That's how it converts kurtosis into energy in the real system. And the way we've drawn it, with time going in one direction and space going in the other direction for differentiations, we're differentiating in space but not in time, we're integrating in time, which means we recover the kurtosis through the space differentiations, and there's no effect, it's incoherent through the timed integrations. That's the fourth cumulant depletion approximated out. Bs there is B squared S is the bandwidth that's the Planck bandwidth, twice the Planck frequency, which is the Planck spectrum is sort of a couple of peaks. It's the second moment of an approximately Gaussian, very closely approximately. The emergent couplings is another way of drawing, which is rather elegant because the integral differential element is one piece there. So, the correlation drift. This process induces a correlation drift. The correlations in the field of the due to the scattering these correlations on the substrate are producing what we call the electromagnetic field. They're inherently Hermitian, and it's got all the right terms in all the right places. That means that this field will generate in its correlations the electromagnetic field. So by applying the correlations of this field to any electron mode you have, you can use the interaction from this field and the electron field itself to produce what the accelerated effects on the electron are, because it has phase effects, and as soon as you put phase effects on an electron, it's moving. It's the same thing as moving in relativity. To have a phase twist is to be moving. Okay. So that means you can see how the electromagnetic field communicates from one electron system to another electron system and induces accelerations. There's one more thing at the end. The resonance effect I've explained, to try to explain to you the way that the electrons resonate, the nature of the equation itself. We have to go through that to get a closer picture of that. Typical stochastic equations you apply to the lower model. Some of these, you go through them if anyone's interested. Anything else I should say here before we pack up? I'd like to mention one more thing. Let's go back through here. Yeah. That's the structural stuff I was telling you about in the three lections. But an interesting challenge comes up regarding curved space. Submariner's relativity. When a submarine is using sonar to look at things, it has to face the fact that temperature gradients in the water will curve the beams, and they do that all the time. So you can see here's an interesting, very tangible case of how a scalar field can cause apparently curved space. If a submariner operates in his observation space, he's got very much the curved space of relativity operating around him. But of course, he says, the very fact that it's curved doesn't mean it is, because we like to think as though there wasn't any seawater there, and that in fact things are in some sort of Euclidean space. He much prefers to do that. He doesn't want to touch a Riemannian space if he could work with a Euclidean space. So the question immediately arises, whether you like it or not, could we do that with ordinary general relativity? And the first thing, don't know. I asked the question for yonks at Oxford in various meetings. Until recently, 6 months ago, I came across the Nash-Kuiper theorems, two of them, C1 and C infinity. Riemannian, all Riemannian, in the definition of the Riemannian space, the manifold, any n-dimensional Riemannian manifold, we'll talk about Riemannian, I'll see that for a moment, any Riemannian manifold in n dimensions can be mapped, can be embedded in an n+1 dimensional Euclidean. space. Okay? That's for, as long as it's differentiable up to the first order. Okay, so as long as we've got bandwidth limitation of any wholesome kind on our functions, you can actually say that if it's Riemannian, then it might still be able to be mapped into an n+1 space. Now, if you introduce a scalar function throughout your n-space Riemannian machinery and treat it as a spare dimension, so it enters as a multiplier in some sense, or a modulator in some sense, then it replicates what you can do with an extra dimension. You don't need an extra dimension, you just need this function to be related properly to the remaining processes you're talking about. And that is what we do with the kurtosis. The kurtosis generates a gravity potential. The kurtosis is directly proportional. There might be a square in it. Forgive me in a moment. It's a very simple relationship, monotonically, to the gravity potential. That's the kurtosis. There are two kurtoses, so you've got some more problem to worry about, the fourth and the sixth, but that's the nature of it. So, we can introduce a scalar function, you've got one, and it will operate on a flat Minkowski space and produce little people like us living in it who think they're in curved space. And what is more, those curved space people, just like the submariner, if they want to, can invert the problem and study it in the flat. That doesn't allow you to treat it as though it's a spherical universe, but it does allow you to handle all the things like lensing and things like that. I think that.
Okay, thanks, Tony.
I might be possible just to mention, this is what the characteristic function for the electrons looks like. And you see the blue at the bottom, negative, and the red at the top, positive. The electrons live just about here, just there, just below the crossing point. And this is the muon, and this is the torr, and the proton and neutron live about here. And if you put it in logs, you can think this way. These are the logs of the frequencies, and you can work out the sort of interactions going on that would allow the baryons to live in that area. They can't live in there or there. They can only live in there, and they do. Okay?
Tony, how do you engineer parametric up conversion?
Well, basically you modulate a reactive, you mean electronics, you modulate a reactive variable and apply your signal to it, you'll get the...
So you're getting magnetic fields, like it's not like kind of up converted photons.
Do you mean in synthesis in electronic circuitry, or do you mean in...
I don't know, I never heard you could do it in like kind of circuits.
Do all the time. All your telephones work with up and down conversion, and they put two of them with the sign reverse to get rid of one or the other. That's exactly what we're talking about.
So
that's Hilbert transform. That's the Hilbert transform.
Okay, thanks. I'll look at it.
Okay, then it's time for a coffee break. That'll take some time to make all this coffee, won't it? You'll need a real expert. Fantastic stuff.